What specific problem does the proposed theory aim to solve in understanding the near block diagonal structure of the Hessian matrix in neural networks? In your answer, elaborate on the gap in existing research that this work addresses.
The proposed theory aims to rigorously explain the near block diagonal structure of the Hessian matrix in neural networks, a phenomenon that has been primarily observed empirically without a solid theoretical foundation for the past 2 decades. Existing research has largely attributed this structure to the cross-entropy (CE) loss function, but this work challenges that perspective by identifying the number of classes as a significant factor influencing the Hessian structure. The gap in current research lies in the lack of a comprehensive theoretical analysis that connects the architectural design of neural networks and the training dynamics to the observed Hessian properties. By revealing 2 forces, static and dynamic, that shape the Hessian structure, this work provides a new understanding of how these factors contribute to the near block diagonal formation, thus filling a critical void in the literature. Ultimately, the findings may also have implications for the design of new optimization algorithms and a deeper understanding of training dynamics in large language models.
How does the proposed methodology work? Illustrate step by step how the authors analyze the Hessian structure, focusing on the roles of static force and dynamic force in shaping this structure during initialization and training stages.
The authors analyze the Hessian structure by identifying 2 key forces, a static force and a dynamic force. The static force, rooted in the architecture design, compresses the cross-neuron components of the Hessian during both the initialization and training stages, leading to a near-block diagonal structure. This is particularly evident in the hidden layer and output layer Hessians, where the authors find that as the number of classes increases, the off-diagonal blocks diminish, reinforcing the block diagonal nature. The dynamic force, which arises during training, further influences the Hessian by gradually erasing initial patterns, such as the block circulant structure observed in the cross-layer components when using cross-entropy loss. The authors rigorously analyze these forces through random matrix theory, providing theoretical results that demonstrate how the Hessian structure evolves as the sample size and input dimensions grow, ultimately leading to a clearer block diagonal form as training progresses.
Can you provide a simple yet illustrative example demonstrating the inner workings of the proposed method? Walk through the steps using a specific case from the paper, such as the analysis of the Hessian in 1 hidden layer networks with CE loss.
To illustrate the inner workings of the proposed method, we can consider the analysis of the Hessian in 1 hidden layer networks with cross-entropy CE loss. In this case, we start by defining the hidden layer Hessian and output layer Hessian, which are derived from the network's weights and the CE loss function. The key observation is that as the number of classes increases, the off-diagonal blocks of the Hessian decay to 0 at a specific rate, leading to a near-block diagonal structure. For instance, when analyzing the hidden layer Hessian, we find that the ratios between off-diagonal and diagonal blocks diminish, indicating that the Hessian becomes increasingly block diagonal as the number of classes grows. This is supported by our theoretical results, which show that the block diagonal structure emerges as the number of classes increases. Additionally, we apply the Lindbergh interpolation principle to handle the asymptotic independence of the random matrices involved, allowing us to rigorously characterize the limit distribution of the Hessian blocks. This systematic approach not only confirms the empirical observations, but also provides a solid theoretical foundation for understanding the Hessian structure in neural networks.
What are the theoretical and practical benefits of understanding the near block diagonal structure of the Hessian? How does this knowledge translate to improvements in training methods or algorithm design for neural networks?
Understanding the near block diagonal structure of the Hessian matrix in neural networks offers both theoretical and practical benefits. Theoretically, it provides insights into the training dynamics of neural networks, revealing that the number of classes is a primary driver of this structure, which challenges previous assumptions attributing it solely to the cross-entropy loss. Practically, this knowledge informs the design of more efficient training methods. For instance, Optimizers like Atom Mini leverage this structure to reduce memory consumption by 50%. Additionally, the near-block diagonal structure enhances the effectiveness of preconditioned methods, such as shampoo and muon, which are utilized in training large models like Gemini 1. 5. And Moonlight. Overall, recognizing this structure can inspire the development of new optimizers and training techniques, ultimately improving the efficiency and performance of neural networks.
How was the method validated or tested within the study? Discuss the experimental design, datasets utilized, and the metrics or benchmarks that demonstrate the effectiveness of the proposed analysis and findings.
The method is validated through a series of empirical studies focusing on the Hessian structure of a one-hidden layer network using a Gaussian synthetic dataset, which allows for generalization beyond specific datasets like CIFAR 100. The experimental design includes varying the input dimension and the number of classes to amplify the effects of cross-layer Hessian components. The study observes the Hessian structure at both random initialization and along the training process, specifically noting the near-block diagonal structures for both mean-squared error, MSE, and cross-entropy, CE loss functions. Key findings include the persistence of near-block diagonal structures during training and the emergence of a block-circulant pattern in cross-layer components when using CE loss, which disappears as training progresses. The effectiveness of the proposed analysis is demonstrated through the consistency of these observations, with theoretical predictions regarding the decay rates of off-diagonal blocks and the clarity of the block diagonal structure as the number of classes increases.
What key results were achieved with this new theoretical framework? Highlight specific outcomes that underscore the implications of the findings in practical scenarios, especially regarding the architecture of neural networks.
The new theoretical framework established in this paper reveals that the near-block diagonal structure of the Hessian matrix in neural networks is significantly influenced by the number of classes, denoted as C, rather than solely by the choice of loss function, such as cross-entropy, CE loss. Specifically, the analysis shows that as C increases, the off-diagonal blocks of the Hessian decay to zero at a rate proportional to C, leading to a clearer block diagonal structure. This finding has practical implications, as it suggests that optimizers like Atom and Atom Mini can be more effective when designed with this architecture in mind, potentially reducing memory consumption and improving training efficiency. Additionally, the identification of both a static force from architecture and a dynamic force from training provides insights into how neural network designs can be optimized for better performance. Overall, the rigorous theoretical analysis not only challenges previous assumptions about the role of CE loss, but also opens avenues for developing new optimization algorithms tailored to the unique Hessian structures of neural networks.